Today, I'm going to talk about the twin dilemma, which is about jammed systems and when a jam system, the question is, when is a jam system not actually jammed? I have divided my talk into three kind of main parts. The first 1/3 of the talk would be mostly me setting up the setting and explaining the math and the terminology. And I'm assuming that most of you will be familiar with these ideas and probably all of it, but I thought it would be good to go over them because sometimes, physicists and mathematicians use different words, different, formalisms for doing the same thing. And I thought it would be good to first introduce what I'm doing here. Then I will tell you about the motivation, which is basically doing a tiling which is similar to all the tilings that you've seen in the past, like talks today and yesterday, but on a very specific type of system. And then I will show you that the rigidity of the tile systems has some surprising results. And then I would tell you why we get those surprising results. All right, so my collaborators for this work are Robert Dennis and Eric Corwin, both from University of Oregon, and they're here. So if you want to chat with them also, please feel free. Okay, so as physicists, when we talk about rigidity of physical systems, most of the times we mean, okay, how does a physical system, respond to external perturbations? If you have some system and you put it under external load, or you perturb it, or you punch it, is it gonna basically preserve its structure and how it was originally, or is it gonna go under dramatic changes in the configuration or basically the structure of the system? The kind of systems that we study have a large variety. They can go from architectural elements like bridges or buildings like this Hancock Tower in Chicago. Whenever I see this tower, I'm like, oh, those just look like, bars that are supporting the load. Another interesting basically system that we study are jammed packings, which are a good model for studying disordered systems at zero temperature. So glasses or glassy systems that are athermal, so which means that temperature is not really playing a role, can be modeled with jammed packings of soft or hard particles, depending on the system. And they're also a good model for studying granular materials in physics. When we go to the biology side of things, which is most of the people who study biophysics, then they use other basically models for studying those type of systems. For example, vertex models are used to study the rigidity or the structure of cell membranes, or basically anything that is a network of cells, or fiber networks, which are usually modeled as just spring networks for studying biopolymers in biology or biophysics. So because of the variety of the systems that we study, we need different proxies, different tools for studying the rigidity of these types of systems. But in most of the physical systems that we study, the rigidity can be really understood by just looking at the degrees of freedom and constraints in the system and how they're playing, how they're basically canceling one another, how they're basically just the interplay between the existing degrees of freedom and the constraints on those degrees of freedom can tell us whether or not if a system is rigid. A good example, which will be the focus of my talk today, is jamming transition. So jamming transition is a rigidity transition that happens in systems with n particles. They can be in any dimensions. We actually study jammed packings from d equals 2 to d equals, we can study d equals infinity, basically. In d dimensions, a system with n particles would have nd degrees of freedom. And depending on whether or not the two particles are interacting or basically overlapping or pushing basically one another, you can have nc number of constraints, or you can call them contacts. When we don't have enough contacts or constraints in the system, so the degrees of freedom are larger than the number of constraints, the system is floppy. When we get to a point where the number of constraints is just equal to the number of degrees of freedom, the system would be rigid and jammed. And we can go further above that and keep increasing the number of constraints by basically, for example, increasing the pressure in the system or increasing the sizes of the particles, which would lead basically to the system forming a lot of new contacts, and the system will be stressed. Jammed packings are first order rigid. And I'm telling you this because I want to tell you that everything I will be showing you today, all the results, are true for systems that are first order rigid. So what we mean by first order is that the non-trivial global motions, the motions of the movements of the nodes or the particles in the system, do not preserve the constraints, but only to the first order. So there are systems that are second order rigid. For example, you can imagine a very under constrained network that is under tension. And because of that tension, it can go through a rigidity transition also, or higher orders of rigidity also exist. So we recently have put this paper on arXiv. If you want to kind of see discussions on higher order rigidity, please check it out. Basically, the idea is that in jammed systems, because they're first order, we can always translate them to networks. And then just by looking at the number of nodes and the number of bonds or the constraints, and then using the constraint counting, which is just as I told you, counting the number of degrees of freedom and then the number of constraints, we can study the rigidity of these systems, and that would be sufficient. Now, one very useful tool, which I'm assuming that most of you are familiar with, but you might know it with different names, is rigidity matrix. So rigidity matrix, or as it's called, compatibility matrix. I think it has other names too. These are the two that I've heard mostly used by physicists and mathematicians. But this is a matrix that is the first derivative of the constraints in the system with respect to degrees of freedom. So for example, in a network, the constraints would be the length of the bonds or the length of the edges in the network. And you can write that length in terms of the degrees of freedom, which would be the positions of the nodes. And then if you take the first derivative for all of the system, you can put it in a matrix form, which is the rigidity matrix. So this rigidity matrix basically tells you which nodes are in contact or which particles are basically interacting. So it also has some information about the connectivity of the system. But it's mainly just a matrix where the rows are the constraints and the columns are the degrees of freedom. And so because each particle has d degrees of freedom, the number of columns would be nd and the number of rows would be just nc, which is the number of constraints. And the way it's written is just that if, for example, particles I and j in a jammed packing are interacting, or nodes I and j are in contact, the information that would go into the row that is representing that contact vector or that bond would be a unit vector that goes from I to j, and then a unit vector that goes from j to I, which is minus the unit vector that goes from I to j. So that's why it has this structure. So this is a very useful matrix because it can be used to study the states of self-stress in the system and find the zero modes. Now, what we mean by zero modes are these motions in the system that do not cost us any energy. Because again, because we mostly model all these systems with spring networks, so there's some energy associated with the system when we look at it from like a physics perspective. So we care about the motions that wouldn't cost us any energy, and zero modes are basically those motions in the system that do not cost any energy. So there are a few equations that I think most people who have basically studied linear response or rigidity theory are familiar with. So if you're in a network or you have two basically interacting particles, let's say I and j, and there's a bond between them, you can move these two particles in some random directions, and that's going to lead to change in the bond length, or basically the overlap that the two particles have. And the matrix that relates these two is that rigidity matrix. So rigidity matrix times the displacements of the nodes or the particles gives you the change in the bond length, or if it's the packing, a jam packing, the overlaps. The transpose of this matrix which also is called, well, I'm just going to call it the transpose of rigidity matrix, but it's also called equilibrium matrix in the literature sometimes. That relates the tensions in the bonds, or the forces between the two particles, the interaction forces between the two particles, to the particles that are on the nodes, so the nodal forces. So the transpose of the rigidity matrix times the tension, the vector of all the tensions on the bonds, gives you the forces on the particles. Now, using this rigidity matrix, which is useful to understand all these properties in the system, and also the rigidity, we can then get to something that is kind of, at the heart of understanding rigidity in the first order rigid systems, which is the Maxwell's count. We can start with the rank nullity theorem. Rank nullity theorem, which is just a theorem in linear algebra that says the rank of any matrix plus the nullity of that matrix equals the dimension of that matrix. So if we use this for the rigidity matrix, we can say, okay, rank of R plus nullity of R is equal to the number of columns in R. Now we can write this rank nullity theorem also for the transpose of the rigidity matrix, because remember that the transpose of the rigidity matrix is relating the tensions on the bonds to the nodal forces, and the rigidity matrix itself is relating the motions of the nodes to the changes in the bond length, or the distance between the two particles. So nullity of R is just a number of zero modes, which I'm going to show with F. Why? Because if you remember from R delta X equals delta L, if the zero modes are all the motions that do not cost us any energy, we can say that, okay, so basically zero modes are those motions of the particles or the nodes that give us zero changes in the bond length or zero changes in the overlaps. Because again, if you remember, energy is usually proportional to either the square or some nonlinear, usually a nonlinear function of this change in the bond length or the overlap of the two particles. Now, nullity of R transpose then is the number of states of self-stress, because again, if you remember, R transpose tau is equal to the nodal forces. So if we want to see what kind of forces we can put on the bonds, what kind of tensions we can put on the bonds without changing or without having any force on the particles, any basically a resultant force on the particles, we can write the equation R transpose tau equals 0, and all the taus that would basically satisfy this equation would be what we call states of self-stress. So states of self-stress are all the ways in which you can put basically forces on the bonds or forces on the overlapping particles without changing the force balance on the particles themselves. Now, I'm not going to talk about the rank of R and rank of R transpose right now and how we can find them, because in any matrix, rank of R is equal to the rank of its transpose, because the maximum number that the rank of a matrix can have is either the minimum of the number of rows or columns. So no matter if you were looking at the matrix or its transpose, it's going to have, the number of rows and columns are going to just be switched. So rank of any matrix is equal to rank of its transpose, which means that I can subtract these two equations at the top. And because rank of R equals to rank of R transpose, these would cancel each other out, and we would be left with nullity of R minus nullity of R transpose equals number of columns in R, which is ND, minus the number of columns in R transpose, which would be the number of rows in R, or NC. And because the nullity of R and nullity of R transpose, we have some physical meaning for them, we can replace them with the zero modes and states of self-stress, and we would get the Maxwell's count. So Maxwell's count basically says that the number of zero modes or motions in the system that would cost zero energy, and the number of states of self-stress are related to basically the difference between the number of degrees of freedom, the total number of degrees of freedom, and the total number of constraints in the system. So let's have a look at this Maxwell's count. This is basically where basically the curiosity that I had starts. So Maxwell's count works for freestanding networks and periodic networks. The only difference would be that in a freestanding network, like the one at the top right that I'm showing, the number of free motions, the motions that would cost a spring network of this type, zero energy, would be D. So in 2D would be 3 because there are 2 translations and there's 1 rotation. But if you have periodic boundaries, which means that you are wrapping this network on a torus, on a donut, which is kind of a way to simulate, an infinitely continuing network. Then the rotational degrees of freedom go away, and the only degrees of freedom that are left in the system are the translations. Now, if the number of zero modes in the system is bigger than D, so this is again, let's say that this is for the periodic systems. For a periodic system, if the number of zero modes is bigger than D, we call the system under constraints or floppy, because it means that there are some internal, floppy modes. There are some internal zero modes that lead to particles being able to rearrange without costing us any energy. If the number of states of self-stress is 0 and F is equal to D, so the only degrees of freedom, the only floppy modes or zero modes that are left in the system are the translations, when we call the system isostatic. And if the number of states of self-stress is bigger than 0, so the system is basically over constraints and there are many, many bonds, and the number of zero modes is D again because of the D translations, we call the system over constrained or over jammed. So these are basically just the definitions that I wanted to give you, because I'm going to refer to these, both the Maxwell's count and these kind of terminology later. Okay, now the question is, what happens to the rigidity of a jammed system if we couple it to another system? We have seen all these amazing talks where, people get some rigid motif and connect it to others and tile the space with it. And here my question is the same basically, but with a jammed system. And let's just start with coupling this jammed system to one more other system. So this can be, of course, done in many, many ways. You can just get 2 random jammed packings and, put them together and then minimize the energy and you would get a new jammed packing, right? But I wanna go a different kind of route. I wanna say, okay, I'm gonna start with a unit cell, which is the main basically network structure of that can come from jam packing or something similar that has the same nature. If I want to produce the periodic boundaries, I can imagine that I have this unit cell in 2D and I'm just putting copies of that unit cell everywhere around that the middle one. And what I'm doing is that I'm making sure that the bonds that we're basically going from this side to this side or top to bottom are basically connected to their equivalent nodes on the copies. Now, what happens if I grab a system like this? So let's say a network that is coming from a jammed packing and redefine its unit cell. So instead of just looking at the system that I originally had, I say, okay, now my new unit cell are these 2 basically networks next to each other, which are the exact copies of one another, but the bonds on the boundaries are a little bit different, but they're the same as the bonds that would basically take that would connect the left side of the cyan cell to the right side of the cyan cell. So what happens to the Maxwell's count if I do something like that? So if we just look at one network, we can say, okay, so a network has n nodes and nc bonds or constraints. We know that the Maxwell's count works for this network. Now, if I just double it, because I'm basically doubling the nodes and doubling the number of bonds or contacts, the n prime, which is the number of nodes in this new system, would be just twice the number of nodes in the previous one. And the number of bonds in this new system would be twice the number of bonds in the original system. Because again, remember that even though we have these, you know, you can imagine that we have these boundary bonds, so something should be different, but it's not, because now, I mean, these were originally connecting the left to the right of this original system, but now they're here, and we have these new bonds that are connecting the left-hand side to the right-hand side of this new system. So the bonds just get doubled, the nodes get doubled, which means that the right-hand side on this Maxwell's equation just gets doubled. For the Maxwell's count to work on these systems, the left-hand side should also double, right? Otherwise, then the system won't be first-order rigid, and then the Maxwell count would be violated. This also works with jammed packings, because again, remember that all these networks that I'm talking about, they're coming from jammed packings at different number of contacts. In a jammed packing, I have n particles, nc contacts. If I just double it, I will have 2 n particles and 2 nc contacts. But what does this twice or doubling both sides of the Maxwell's equation imply? Does that mean that because the left-hand side of the equation, which is 2 times f minus s, is doubled, does it just mean that both the degrees of freedom and the states of self-stress have doubled, or is there something else going on? If somebody had asked me before we actually went and, you know, did this, you know, my first question would be, yeah, probably that's what happens, that, you know, if you double everything in the system, because it's exactly the same system, both the number of the floppy modes or zero modes f and the number of states of self-stress will just double. But interestingly, we went and looked at a bunch of networks and jammed packings that basically were equivalent to these networks. And we realized that this is not always the case. So doubling the left-hand side of the equation, the Maxwell's equation, does not mean that both terms are getting doubled, but there's a different story. Okay, it turns out that the way the number of zero modes and the number of states of self-stress in the new system change actually depends on how many states of self-stress you have in the system and how far from isostatic you are. If you start from an isostatic system, which again, if you remember the definition, it meant that the number of zero modes is just equal to the d translations, and there are 0 states of self-stress, and you double the network or the packing. I mean, you can't really have packings that are isostatic, but if you translate them to networks and then remove one bond, you can get, you know, isostatic networks that are coming from jamming. Anyways, if you just double that network and make sure that the boundaries are correctly attached to one another, you will see that now there are 2D new zero modes in the system, and the states of self-stress remain 0. So this kind of, if we had just looked at this, we would be like, yeah, that's exactly what's happening. Both F and S are just getting doubled. But when we go to isostatic plus 1 state of self-stress, so F is equal to D, because again, this is a rigid system with only zero modes, and the only zero modes that are available to the system are the D translations. But now there is this new state of self-stress, or there is this 1 state of self-stress that makes the system, you know, basically jammed or stressed. If we double that, what happens is that the number of zero modes and the number of states of self-stress do not double. The number of states of self-stress remains the same, and the number of zero modes doubles, changes in a way that it will make sure that, you know, this equation on the right-hand side of this table, which says that's f prime minus s prime is double f minus s, is satisfied. So for example, in 2D, with a network in 2D, if f is equal to 2 and s is equal to 1, when you basically double the unit cell and make sure that it's, you know, it's replicated in a correct way, and the boundary conditions are all satisfied in the way that were satisfied in the original network, you would get 1 new zero mode, but the states of self-stress will not double. They will not change. The new system still has 1 state of self-stress, but also 1 new zero mode. Now, if you go to isostatic plus 2 states of self-stress, interestingly, you'll see that at least in 2D, nothing changes, even though the new number of zero modes would be 2D minus 2, and the number of states of self-stress remains the same. So when D is equal to 2, F prime is going to remain 2. So which basically means that when you have two states of self-stress, for example, in like in a Kagame lattice or in a a square lattice, after you double the unit cell and then you connect it to its original copy, the new system, the new doubled unit cell will still have two total floppy modes or zero modes and two states of self-stress. Now, if you continue going up, so if you go to isostatic plus 3, again, F is equal to 2, now S is equal to 3. Interestingly, the number of zero modes do not change anymore as you double, but the number of states of self-stress go up. So it's not that by just tiling the system or like tiling or even making one copy of a jammed network or jammed packing and attaching it to itself is always going to make, you know, both the floppy modes or the zero modes and the states of self-stress double. It totally depends on where from the isostatic you are and how many states of self-stress are in the system. So this was pretty interesting for us because we were wondering, okay, where is this coming from? Because this is very systematically changing. It's not something that sometimes happens and sometimes doesn't. It's a very systematic change. So there must be something, you know, something mathematical about it that can explain where these zero modes are coming from when the basically number of states of self-stress is smaller than D. Because we also checked it with 3D systems, both packings and networks, and we see the same trend basically. And I think we have checked a few 4D systems too, and we see a similar trend. But the basic trend is that whenever the number of states of self-stress in the system are smaller than D, which is the dimension of the space, replicating a system and attaching it to itself will increase the number of zero modes in the system, but will not change the number of states of self-stress. As soon as you get to the point where they're the same, so the number of states of self-stress is equal to D, then nothing changes in the system, which is actually the number of floppy modes are actually changing. But, I mean, the equations are in a way that it seems like it's not changing. And as soon as you go above that, then by replicating a jammed packing or a jammed network, it's the states of self-stress that's increased. Now, there is some previous work that shows that sometimes, you know, if you have a very over-constrained jammed packing and then you tile the space with it, sometimes there's like one new zero mode appears, but these kind of zero modes are usually associated with how mechanically stable the system is, and they can go like we can probably understand them we can usually understand them using, you know, the eigenvalues of the Hessian of the system, which are the second derivatives of the energy, but that's not really a systematic change. We see those kind of zero modes that sometimes appear in tiled, you know, in systems that are basically tiling of jam packings. Sometimes we see them, sometimes we don't see them, but there's never really a systematic trend, and they're usually appear when the system becomes marginally stable instead of being just the way the basically retaining the stability that it had when we make this this kind of copying. We have examples that this also happens in systems where we have very special symmetries. So when the system is very symmetric and along some like axes, and then you replicate it, you might see that, oh, one new zero mode appeared. But those are, again, not systematic. This is kind of like something that has different nature from those kind of zero modes that appear, because this is very systematic and it happens in every system that we've studied every time. All right, so now you might wonder what these zero modes look like. I'm going to show you one example, which is a 2D system copied and replicated along the X and Y axis. So you can see that if I start from this network on the left and copy it on the along the X direction and then attach it to itself, the new zero mode that appears is very interesting, because this node here, this node number 7, is equivalent to this node number 24, and you can see that the way this has moved, So the blue one is the original, and the red is after I have applied the zero mode to the nodes. You can see that the 7 has moved in this direction, and the 24th, which is its equivalent in this new copy, has moved it exactly in the opposite direction. You can see the same thing if you copy it along, the y direction, or basically in any other direction. So basically what's happening is that the movements that are appearing in these zero modes are in a way that the sum of the motions of all the particles that are the copies of the original particle, the sum of the motions will add up to 0. And you can do that with not just one copy. You can do it with 2 copy, 3 copy, or infinite number of copies. But what is fascinating kind of here is that per each copy that you add, if there's one state of self-stress in a 2D system, there will be one new zero mode added to the system. All right, so now what do these zero modes mean? These zero modes imply something very important, which is this theorem that my collaborator Robert Dennis has written and has proved. It basically says that when we have a jammed system, if the number of states of self-stress is smaller than d, copying or replicating the system and attaching it along some arbitrary boundary x will make it unjam. Will introduce new zero modes to the system, which will make it unjam. Now, I'm gonna present you a proof that is kind of like mathematical. I hope you bear with me, but this is very important. This is very interesting because usually in jammed packings, as long as there's even one state of self-stress, we call those packings jammed and they become fully rigid. But this basically shows that when your number of states of self-stress is smaller than d, your system might look jammed, but if you just replicate it, along any boundary, which would mean that you are making it infinite, making it go to infinity, and basically you're applying that periodicity to the system, it will unjam. So maybe truly jammed systems should have states of self-stress that are bigger than d. Now, what's the proof? Okay, so the proof goes like this. I'm going to walk you through the steps of the proof. If you have any questions or if there's any point along the proof that you don't understand, please stop me and ask me. But the proof is that you can write the rigidity matrix of any first order rigid system, like I showed you, which is this matrix on the left. And then you can break it into different parts. So now you might ask, okay, this looks kind of arbitrary. Why are you breaking like this? I'll show you later why I'm breaking it like this. But for now, just imagine that I have gotten the rigidity matrix of a system and I break it into this like blocks of matrices where RC is all the bonds that are related to the central bonds. So anything like this hot pink bond or anything that's in the middle that is not attached to the boundary or is not going across the boundary, we can write them all, like we can all collect them and rearrange them in a way that they're all in this block. Then we can write, then we can basically put together all the bonds that are on the perimeter, but they're not going across the bond, like across the system. So these are the bonds that are attached to the nodes that are on the perimeter, but they're not basically going across the boundary. We can write them again as some other matrix, which is RP. And then because of this structure of the rigidity matrix, which shows that basically bonds that go from I to J will have this Nij, and bonds that go from J to I will have this minus Nij. So basically this Nij and minus Nij are the same vectors, but just with opposite directions. These would be the bonds that go from the perimeter nodes to the perimeter nodes on the other side, which are basically the bonds that are crossing the boundary. And then we can break it into two basically matrices, which is the ones that go in one direction and the bonds that go in the opposite direction. It doesn't have to be right to left or left to right. It's just that, I'm basically making this distinction to just show you that I'm saying that if for example, one end of the bond is on the left-hand side and the other is on the right-hand side. The other Nij that appears, I will call that going from left to right, right to left, and then I can break it into two matrices. Now, we are going to introduce an auxiliary matrix. Let's call it RDHC. This auxiliary matrix is basically very similar to this rigidity matrix, but the only difference is that in this boundary bonds that were presented as RB2 plus RB1, we have changed the sign of this RB1. Now you might say, okay, what is this RDHC and why are you defining it like this? This is just an auxiliary matrix. It doesn't have any physical meaning, so it's not really, it's not the same as the rigidity matrix, and it's not really describing anything physical in the system. It's just a matrix that I will use later in this proof to show you why it's useful. All right. So now let's go back and look at the ranks of R and this RDHC. So when we have a periodic system, if it's jammed, the rank of R should be ND minus D. Again, this is just from rank nullity theorem, rank of R plus the nullity of R, which for a rigid system would be D, equals the number of columns in R. So rank of R equals ND minus D. Now, what can we tell about the rank of the DHC matrix? We can't really tell what the rank of the DHC matrix is, whether or not if it's full rank or it's not. I mean, we know that the rigidity matrix is not full rank because of these translations that exist in the system, that are available to the system. But we might think that, okay, because we're breaking that translational symmetry in the system, then the RDHC should not have those. I mean, we shouldn't have to subtract those D translations from the system, but we really don't know. So all we can say about the rank of this DHC matrix is that the maximum number that it can have is the minimum of the number of columns and the number of rows. And because this RDHC has basically the same dimension as the R, then the number of columns and rows are just ND and NC. So all we can say about the rank of this RDHC right now is just its maximum is the minimum of ND and NC. All right. Now, we also know that rank of R equals number of constraints in the system minus the state of self-stress. Again, this is, I can say, okay, if rank of R is ND minus D, from Maxwell's count, I know that ND minus D would be equal to NC minus S. So I can say that, okay, rank of R is also NC minus S, where S is the number of states of self-stress. So I can then replace this NC that I have appearing in the rank of RDHC with this information that I have here, which is rank of R equals NC minus S. And I will get to this information, which is the maximum number that the rank of RDHC can have is the minimum of ND and ND plus S minus D. Now, what happens is that if S is smaller than D, which is the case that I showed to you in my systems, where the number of states of self-stress were smaller than the number of translational degrees of freedom during the system, then we will know that then this term here will be negative, and therefore the minimum of ND and ND minus something will be that ND minus something. So from that we can say that, okay, then the maximum of rank of RDHC would be ND. All right, so which would mean that the maximum rank that RDHC can have, would be for it to be full rank. So this basically tells us that the rank of R plus the rank of RDHC should be smaller than 2ND minus D. So basically, I'm just replacing whatever that I have for rank of R and whatever I have information about the max of rank of RDHC, which is the maximum number it can have is ND. Therefore, the rank of R plus the rank of RDHC is smaller than 2ND minus D. Okay, now I know that this is really math intense, and I mean, I'm assuming that most of you probably are bored and are not even following this, but it doesn't matter because at this point you don't need to remember all the proof that I showed you. All you need to kind of remember is that in systems where the number of states of self-stress is smaller than the number of translational degrees of freedom, or translational zero modes, we will have the rank of this R matrix, rigidity matrix, plus the rank of this auxiliary matrix that we defined, equal than 2nd minus d. Now, why do we care about the rank of this auxiliary matrix? This is where basically the importance of this auxiliary matrix comes into play. So why do we care? Like, what does this tell us about the duplicated matrices, the matrices that we get from, you know, attaching a jammed packing to its copy? There is there's a proof again done by Robert, and I can show you the proof later if you're interested. But we can basically show that if you have the rigidity matrix with singular values that are set of singular values sigma, and then look at the singular, assume that the RDHC has singular values epsilon, you can show that the rigidity matrix of the duplicated system would look like this, and we'll have singular values, which is basically the union of these two sets, which are the singular values, the rigidity matrix, and this auxiliary matrix that we're defining by just basically flipping the sign of the boundary bonds. So this is important because the number of singular values is the rank of basically the matrix. Therefore, just by knowing this part, which is, okay, if you have the singular values of the rigidity matrix and the singular values of this auxiliary or DHC matrix, you can find the singular values of the rigidity matrix of the duplicated system, which would mean that the rank of this duplicated system's rigidity matrix, or RD, is equal to the rank of R plus rank of RDHC, because again, the singular values of RD are just the union of the two sets, which is one of them is the singular values of R, the other one is the singular values of RDHC. And from that basically a proof, we know that rank of R plus rank of this RDHC is smaller than this value. So basically what this means is that whenever you have a system and then you duplicate it, and then look at its rigidity matrix, which is RD, its rank will always be smaller than 2nd minus d. So what does this mean? This means that if I have a jammed packing with n particles, and if I want it to be jammed and rigid, the only degrees of freedom or only floppy modes or zero modes, whatever you want to call them, that I'm allowing to the system would be the D translations. Therefore, for a jammed packing, the rank of the rigidity matrix will always be ND minus D. And the only zero modes that are available are these D translations. When I duplicate it, when I copy it and attach its copy to itself, if S is equal than, if S is smaller than D, which would mean that the rank of this the rigidity matrix of this duplicated system would be smaller than 2ND minus D, which basically means that if I was just looking at some arbitrary, ordinary jammed packing with 2N particles, and if it had, you know, one state of self-stress, its rank would be 2ND minus D. So the fact that in this system, the rank of the duplicated system is always smaller than 2ND minus D means that there are some new basically zero modes, some new zero energy costing motions in the system that are forming, and they're, I mean, you cannot get rid of them. I mean, they would always exist just because of how basically the rigidity playing a role, and how, you know, the rigidity matrix is playing a role in these systems. So this basically is kind of the end of my talk, but it also, this is basically just all I have to tell you, that we see that when we replicate a jammed system and attach it to its copy, the number of zero modes in state of self-stress do not just double. They change in an unexpected way, but it's very systematic. We have seen that when the system is at isostatic +1, +2, all the way to D minus 1, by adding each copy, there are new zero modes that get added to the system. but state of self-stress do not change. When the network or the system or the jam packing is at isostatic plus d bonds, by adding the copies, neither the number of states of self-stress nor the number of zero modes change. And finally, when the system is above, has more than d states of self-stress, and basically is above isostatic plus d, by adding copies, you would never get new zero modes. Instead, you would get new states of self-stress. And the way you can find those states of self-stress just can be calculated from the Maxwell's count, because the system is not unjamming, and you know that the only zero modes that are allowed in the system are still the D translational zero modes. Therefore, just by plugging in all the information into the Maxwell's count, you can see that basically the states of, you can calculate the state of self-stress. So in conclusion, we can see that, okay, so when we have a jammed system, as long as the states of self-stress are smaller than these states of self-stress, it unjams if we replicate it and copy it to itself across any boundary. Now, this then raises the question of why this is the case. I mean, yeah, we have a mathematical description for it, but what's happening really from a physics point of view? And we're thinking that these are basically the shear degrees of freedom, because if you have a d-dimensional system and I mean, you can shear it in d ways. Like, for example, in 2 dimensions, the system will have two shear degrees of freedom. And when you're attaching a copy to itself, you are basically removing the boundary that was in there previously, and therefore you're introducing this like new shear modes into the system that are showing themselves in the form of these new zero modes, or new zero, basically these new floppy modes. But this is something that we're still exploring. We would like to know if there's really a relation between these new zero modes and the shear degrees of freedom in the system. With that, I would like to thank my collaborators, Robert Dennis and Eric Corwin. I didn't show slides from our higher order rigidity work, but my collaborators for that were Ojan, Lisa, and Christian. And I've had fruitful discussions with Sydney Nagel. So thank you. I would take any questions now.
Thank you, Varda. So questions from the audience. Ciprian.
I have some remarks and requests for clarification. Mm-hmm. So in the periodic context, we have already in our periodic frameworks and flexibility of 2010, this question of behavior of a framework and relaxation of periodicity. Mm-hmm. So what you described here as a doubling is you just relax the periodicity lattice in one direction by an index 2 sublattice. But the problem can be formulated for any relaxation. And it's obvious that the deformations may increase because you have less, you have relaxed the constraints. So that phenomenon is in my opinion, very interesting to have a control over what happens over successive relaxations. I think it's a very difficult problem, and your talk is clearly in that region. Now, I want to point out that in dimension 2, we have addressed the problem of this, what happens to the stresses and the relaxation. And it's an important step in our results in discrete and computational geometry paper of 2015 called Lifting and Stresses for Planar Periodic Frameworks. And there is a precise statement and proof that upon relaxation, periodic stresses can only increase in dimension. So all that was previously there remains there. So if I may speak of a paradox at the level of language, you say to someone, relax, the stress will go, but this theorem says, relax, the stress won't go. So we have, and I would mention for your attention, we have this precise statement in dimension 2 and with proof next to it, saying that stresses persist under relaxation in the periodic context, and our periodic context is allowing the periodicity lattice to vary. So and my question is, when you speak of periodicity and floppy modes, do you consider the lattice fixed or allowed to change?
No, we're fixing the lattice vectors here. We would do that if we are shear stabilizing the system. So basically, when we're shear stabilizing the system, we would allow the lattice vectors to change, and then we would treat them also as degrees of freedom in the Hessian. And we would, when we're minimizing the energy, we would also minimize the energy with respect to those. So in these cases, no, we're actually fixing the lattice vectors.
Yes,
and
so this means our result is even more general than what you considered. And with your permission, I will send you the precise reference.
Oh, definitely, please do. Yes, I would love to look at that work. But also, one thing that I should say is that, I mean, if we just look at the rigidity matrix, and because the way we calculate the number of states of self-stress in the system is just they're basically the number of zero modes of the R transpose matrix. Or the nullity of the R transpose matrix. So if we just look at that, as you can see, the stresses do not go away upon replication. I mean, when we are below the states of self-stress, they do not increase. They only increase when we're above these states of self-stress. But when we're below that, we're not saying that they do go away. Now, I'm using a terminology unjammed here, because in a jammed system, I mean, it's a little bit different, because in a jammed system, when you introduce something in the system that is like a degree of freedom, the system is either jammed and has a state of self-stress or multiple states of self-stress that span the entire system, or it unjams and there's no stress in the system. But when we say unjammed, if we just look at the rigidity matrix of the jammed packings, we will see that there is still a state of self-stress, but it's because of but in these physical systems, the rigidity matrix, also you need more terms in the energy. You need to consider more higher orders of the energy. And when you look at the zero modes of the Hessian, the full Hessian, not just the Gramian term, which is built upon this rigidity matrix, you will see that there are new zero modes appearing, and therefore, it looks like the states of self-stress is going away because the system is unjamming. But if we just look at from a mathematical point of view, the stress is actually there. Or if we just look at the networks, on the network that is built upon a jam packing.
It's clear to me that there's a need for a very meticulous dictionary from the language you use and the language in our papers. But my wish was to point out that in some version of what you consider, we have proven a result of this nature. And I will send you.
Yes, please do.
Can I ask a quick question about that paper as well? Yeah, I'd also be very interested in seeing it. But we have I think this might be what you're talking about. For our systems, we talked about these RB1 and RB2 bonds. And these are sort of, special because they are the ones that cross our box boundary. But as far as the proof is concerned, these RB1 and RB2 could be any subset of bonds in the system, and everything works the same way. It's just less, I guess, clear what it means to replicate across those bonds in terms of drawing the thing.
Okay.
Yeah, you can basically replicate it along any bonds, even somewhere in the middle of the system. That's, I think.
Thank you.
And yeah, our results would be true even if you replicate not across the boundaries on the sides, but any boundary. But
okay, any other questions?
Yes, this was a very nice talk. Thank you. I'm having a little trouble translating from the math to the physics. So if I were looking for some sort of physical signature or physical significance of this interesting result, is there anything that's evident there?
I would say the most interesting thing for me, at least, was the fact that, when do we consider the jamming transition or jammed packings actually rigid? Because there is some literature that shows that if you do not shear stabilize jammed packings, they're not really jammed. They're not, what they do is not showing that by replicating, but there are some discussions that show that if truly jammed systems, or the actual jamming happens when you have at least these states of self-stress and above that. But in the physics community, we do consider anything that has, at least one state of self-stress a jammed or critically jammed packing. So I think this we're hoping that we can move these results in the direction and kind of, see if these are related to that shear stabilization, and therefore say that, yes, this is another kind of, evidence that shows that packings of particles with states of self-stress fewer than D are not truly jammed. The true jamming happens at the D states of self-stress and above.
Okay, thank you. And if I have time, there's also one technical question I had about the proof. So I didn't follow every step, but there was a point where you went from writing down maxima and minima to an inequality where it wasn't clear to me why it was a strict inequality.
I think there was a mistake there. I should look at it because I was like, oh no, I think there's a mistake.
Okay, yeah, because there was something where it was max. So I'm like, oh, so there should be less than or equal to it.
Yeah. There was a mistake, but I'll fix it, and then I'll be in the gather.town, and we can talk about it. So.
Oh, I'd love to talk more. Thank you.
Yeah.
Daniel.
Hey, so, okay, so I have a question to preface that. So it seems like one way to think about this whole situation where you have these like periodic frameworks is you have like one graph that you sort of, I'm thinking in the plane, just for example, like you have a graph, and you put copies of it like all over the plane, like according to a lattice. And maybe one way to sort of enforce your periodicity is just to like for every vertex, put a bar attaching it to like every single image of it under your lattice. So I'm thinking about like a periodic framework is like you have your graph, and then you have this Z2 acting on your point configuration. So like your original sort of like fundamental domain or whatever you want to. I don't know what the right language in the physics world is, but you sort of think about just like its image under Z2 all over the place, and you can enforce this periodicity just by attaching each vertex to like everything in its orbit. And then it sounds like what you're doing by like doubling this domain is you're just like now dropping all of these bars that go between, say, your configuration and then its image under just like your translation to the right. And it seems like, by dropping all these bars, you can now like create a motion. So then from this perspective, it seems like, well, okay, maybe when you do that, it doesn't become flexible. But like, what if you took like, what if you took more? What if instead of doing 2, you took like, 4 in like the configuration of a square? What if you took 9? And it seems like maybe by dropping enough bars in this way of looking at it, you can always get to something floppy or flexible.
So,
is that first of all?
Dan, I was actually gonna ask about this.
Well, let me first make sure that I understand what you mean by dropping the balls, because we're not really dropping any bars here.
What I just said before. You instead of the initial lattice of periodicity, you consider sublattice.
Yeah.
So that's what you probably suggest by the word dropping. Yes,
same idea.
That's the relaxation problem I stated before, and it's certainly a very important one, and it's formulated already in our paper of 2010.
So Lewis Thuran and Simon Mailstein have answered this sort of question on an idea called ultra-rigidity.
Mm-hmm.
So it's basically, it says no matter how you relax the lattice, you're still going to be periodically rigid. I think the paper's just called ultra-periodic rigidity, and that was going to be my comment. But then Dan started talking about exactly what I was going to mention. But yeah, so I think that they have a combinatorial characterization of it. But obviously, it's a generic property. Generic's not the right word, but yeah.
Okay, so that's a statement that no matter how you relax it, it's gonna be rigid.
Yeah.
So what's the definition of rigidity there? Because in jamming, if you have any internal, basically 0 modes, the system will not be jammed or rigid. So so I'm trying to understand if rigidity here means just the existence of states of self-stress, and because the states of self-stress or stresses are not going away, then you're saying that, yeah, no matter how we relax it and no matter how many copies we're making, it's always gonna basically preserve those states of self-stress, and if you're far above isostatic, you're always gonna even get extra. Is that what you mean, and what they mean by being
I do, but I'm talking, I guess the thing they deal with is frameworks instead of jammings. So you don't just, two things, you're also assuming that they can't get any closer, but they can't get any further apart as well. So it's a slightly different condition. So is different, but it's kind of very linked. It is very linked.
Okay, yeah, that's another paper I should look at.
If I could jump in, when we see, basically what we see is that if you, no matter how many times you double and in how many directions, if you begin with fewer than d excess contacts, you will always create these new 0 modes. Whereas if you begin with d or greater excess contacts, you will never create 0 modes. One thing that's really fascinating, though, is that as you keep doubling, you can of course create you're creating new modes, and those new modes can have, you know, essentially whatever frequency you'd like associated with them, or whatever energy you'd like associated with them. And one thing that we find is that for certain packings in certain directions, you can double and you can find anomalously low energy modes. So for example, if you have a given, you know, packing or network or framework, however you want to call it, and then you double, say, you know, 6 times in the X direction and 9 times in the Y direction, then you can end up with a configuration that has an extraordinarily low energy mode, but low energy, but still not zero. So there's a lot of, I think, interesting structure to be found through these doubling processes.
So a short comment here. I mean, obviously doubling is the simplest case to explore, but for the general result for arbitrary relaxations, you have to look at all primes. So it's not true that you, by relaxing, say, with index P, odd prime, you can find that relaxation via doublings, or mean a relaxation of that relaxation. So
sorry, yes, I misspoke. We were doing you know, multiplications by a whole range. We weren't just doing doublings.
Yeah. I mean, I'm showing actually on the screen that this. I mean, we haven't just done doubling. We have done, you know, we can basically build an n by n or n by m new lattice by repeating these along x and y, or in 3D along x and y and z directions. And the results that I showed you here, not here, sorry, here and here, these are per copy. So if I'm getting one extra zero mode in 2D after adding 1 copy, if I add the 3rd copy, I'm going to get 2 extra zero modes. If I add 100 copies, I'm going to get 100 extra zero modes. So if I start with a network or a packing that has only 2 zero modes of translations, which are trivial rigid motions, and then add 100 copies to that, that's going to have 102 zero modes, the new system. So very, very very floppy, I would say.
So you say you do m by n. There's nothing stopping you from doing weirder shapes like L shapes or something, or maybe even twisted boundary conditions like a Mobius strip.
So the reason we didn't do any L shapes, for example, is that, again, we are after, so here, after we make this new unit cell, our new unit cell, then we use that to create, you know, boundary conditions, periodic boundary conditions. So we're always wrapping these on a torus, and I'm not sure if there's a way to wrap an L-shaped structure on a torus.
So
maybe there is, but
we haven't tried any of the exotic L-shaped stuff, but we did actually play with the, you know, twisted boundary conditions.
yeah.
And this was something that Cam Dennis put together, and the conclusion was everything is the same with those twisted boundaries.